Okay, for this video, we are going to try to figure out what is the pH of a 0.250 molar ammonium chloride solution. Ammonium, NH4+, can be visualized as the conjugate acid of NH3, which is a weak base, which is why we know its Kb value. Cl is essentially just an ion that is happy to float around. Like if you have HCl, it is a strong acid because the H plus comes off and it acts as an acid, and the chlorine is happy to just float around. It doesn't have a reverse reaction, so Cl is happy to just be ignored the entire time. So we're going to visualize this as NH4+ reacting with water, and because this is the conjugate acid of this base, we're going to treat it as an acid. So I'm going to label it here, weak acid. Because it's an acid, it's going to give up an H+, and we're going to form NH3. And look, they're conjugate acid base pairs, just like they would have been if you'd started with this as a base. And this is going to receive an H+ and become H3O+, which makes sense because this is an acid. Okay, just like we did on the previous problem, the previous video, we don't know the Ka for this, but we can solve for it. Okay. So we can't check the assumption until we solve for Ka. So Ka times Kb equals Kw. We know Kb, Kw is a constant, so Ka is, we're basically dividing Kb to the other side. Kw is a constant. It is 1.0 times 10 to the negative 14th. Kb of the conjugate base is 1.8 times 10 to the negative 5th. When you plug this all in, it comes out to 5.6 times 10 to the negative 10th, a fairly low Ka value. To check our assumption, what we need to do, take the concentration of the NH4+, which is 0.25, and divide it by our Ka value. And I'm assuming this is going to come out to be bigger than 100, but we need to check it. And yeah, it's, I don't know, what is that, 400 billion? It's basically 4.4 times 10 to the 368. Yeah, I think we're good. Bigger than 100. So no quadratic. Okay. Otherwise, the rest of the problem is going to be the same as any other weak acid, weak base problem. Okay. So we know the initial, the change, the equilibrium of the initial is 0.250. If we ignore the water, we're starting out with 0 of those things. Okay. This is going to decrease by some amount, increase by some amount. This will be 0.250 minus x, this will be x, and this will be x. The Ka value describes the equilibrium, so it'll be the NH3 times the H3O+ divided by the NH4. Okay, I'm just going to put all the numbers in, so 5.6 times 10 to the negative 10th is equal to x squared, because these things are both on top, I'm just multiplying them together, divided by 0.25. That minus x is going to disappear because our assumption was true. So, to solve for x, we're going to multiply this over and then take the square root. So let's plug in some numbers and see what we get. So, square root 0.250 times 5.6 e to the negative 10th. I got 1.18 times 10 to the negative 5th. Okay. This is the molarity of our H3O+. So because this is an acid, we can just take the negative log of this to get pH. See what we get. That's the number I had up there, so I'm just going to hit negative log of our answer. And I got 4.93. So, again, overviewing this problem, essentially because we have NH4+, which can be visualized as the conjugate acid of this base, we treat it as a weak acid problem. Because it is a weak acid, we'll have to solve for Ka because it was not given to us. But after that, it's literally just like any other weak acid problem that we've done. All right, thanks.